The next talk is on the status of conservation laws in physics and their implication for semiclassical gravity, which is presented by Elias Okon.
Thank you. Hello everybody. This talk is based on joint work with Tim Modlin from NYU and Daniel Sudarsky, who's our next speaker. Alright, so let's start. Well, the starting point of this talk is an observation, which is the fact that often some principles which are considered essential at some stage in the development of physics somehow continue to be regarded as such well after the philosophical, let's say, reasons for doing so are discarded. And this seems to be the case with certain conservation laws and in particular with energy conservation. So what I will do in this talk is to explore the status of energy conservation. It's just we could do this with some other conservation law. We chose energy. And we explore the status of energy conservation in the context of our best physical theories. And then we will examine implications of our analysis for the semi-classical gravity problem. Okay, so the plan is the following. We'll start considering the classical context, and we'll go over it quickly. So we'll say a few more or less standard things about that, and then we'll jump to the quantum context, in which I think we will say some non-trivial things, and we will start with the non-relativistic case, then we'll go to the relativistic one, and then we'll finish with alternative interpretations to the standard quantum formalism. Alright, so let's start with the classical context. As all you know, in 1915, Nether proved this famous theorem, which states that every differentiable symmetry of the action of a Lagrangian system generates a conserved quantity. And what I want to point out is that these conserved quantities that are extracted through Nether's theorem are not like real substances or real things out there. What they are some sort of like mathematical shadows or something like that arise from symmetries in the Lagrangian. So, in particular, we usually associate these conserved quantities with individual bodies. So, for example, we think of energy as present in some body running over there. But in fact, these conserved quantities are not properties of that object, but are facts that go further, vastly outrun the state of the concrete bodies we are associating these conserved quantities to. Another important thing to note is that, according to this view, of course, there are as many energies as there are temporal symmetries in a system. So, for example, in Minkowski, we have an infinite number of temporal symmetries, so we have an infinite number of these energies that can be assigned. What happens when we go to general relativity? Well, this infinite number of energies generically reduces to zero, because in the context of general relativity, and like in general and in particular in our universe, there are no time-like killing fields. So if we don't have temporal symmetries, there are no energies to be associated. In general relativity and in our universe, there is no reason to expect any exact principle of energy conservation to obtain. It's important to notice that the energy momentum tensor, of course, continues to be divergenceless, but the point is that the fact cannot be used to construct an exact conserved quantity in the absence of a time-like killing vector field. Of course, one can always construct approximate conserved quantities if one has approximate temporal killing fields, but if there's no exact killing field, there's no conservation of energy. Just to conclude about this, the classical context, I think that given all we've said, and if you think about it a bit, one should, at least for now in the classical context, have an attitude towards energy conservation similar to the attitude one has towards Euclidean geometry. So the idea is that before general relativity, we thought that Euclidean geometry was a correct description of our universe. Now we know it isn't, but we still know that Euclidean geometry under certain conditions is a very good approximation to what's going on, and the same regarding conservation of energy. It can be very useful to know that energy is approximately conserved in certain systems to do calculations, etc., but that does not mean that there's an exact energy conservation going on out there in the world. Okay, so let's move on to the quantum context. Let's start with non-relativistic quantum mechanics. And so the first thing that comes to mind when one starts thinking about energy conservation in this context is that Hermitian operators that commute with the Hamiltonian are usually called constants of the motion. That seems to be related with something that is conserved. However, if one thinks about it a bit, one realizes that all this means, having an operator that commutes with the Hamiltonian, all that means is that during unitary evolution, the expectation values of these operators and the Born probabilities associated with them are conserved. So this might suggest that there are things that are conserved only on average, because we're talking about these Born probabilities, about expectation values, but it doesn't seem to say anything about things being exactly conserved in each system. And moreover, as I said, these things are conserved during unitary evolution, but during measurements, generically, expectation values do change. So what's going on? Are things conserved or not in quantum mechanics? So to explore this, let's consider a simple example. So we take a system and we prepare it on this particular state where E1 and E2 are energy eigenstates, so we have this superposition. And well, first off, if that is the state, we know that the expectation value initially of energy is this combination. But of course, if we go and measure the energy of the system, we'll get either E1 or E2 as a result. So after the measurement, the expectation value is either E1 or E2. So, question, does this imply that energy is not conserved during measurements? And well, to begin with, I think that's a difficult question to answer, because it's not that we started with in some state in which energy is well defined and we jump to another state in which energy is also well defined but is different. What's going on is that we start in a state in which energy simply does not have a well defined value, and we jump to a value to a final state in which it does. So it's not clear if this implies that energy is either conserved or not. But we can circumvent this complication by considering a simple two-step process, which is the following. So instead of starting in this superposition, we start at E1. So the energy at the initial state does have a well-defined value. And what we first do is to measure some property that does not commute with Hamiltonian. Clearly, if we do that, this will leave the system in some superposition of energy eigenstates. For simplicity, suppose that this superposition of energy eigenstates is precisely this one we started with in the previous example. So just for simplicity, we'll do that. And then the next step is to go and measure energy. Of course, if we do that, we'll have 50% chance of ending up in E2, which is a different energy than the one that we started with. So it seems that, well, now we managed to go from a well-defined energy to a different well-defined energy. So have we shown that energy is not conserved in quantum mechanics? Not so fast. It's not that simple. Of course, in all I've said so far, we've left out completely the measurement apparatuses. So that seems to be a problem. And it might seem that it may well be that if we include the measurement apparatuses, then energy conservation will be exactly restored. After all, of course, we expect energy to be conserved in closed systems, and if we leave out part of the system, it's no surprise that energy could be not conserved. So, what happens if we do include the measurement apparatuses? So, including them could lead to exact energy conservation, and things get a bit murky at this point, because actually to respond to that question, what would need to decide what to do with the measurement apparatuses, and in particular what one would need to answer if, or to determine if they can or cannot be described quantum mechanically. And well, there seem to be two options. If one with Bohr answers no to that question, with Bohr one declares that measurement apparatuses cannot be described quantum mechanically, then one cannot really prove that energy is conserved if one includes these measurement apparatuses. One can only just assume that that is the case if one wants to. Because, I mean, if you cannot describe these measurement apparatuses quantum mechanically, then you will have no mechanism to explain how energy fluxes go from the quantum part to the classical part, and you cannot really check if energy is conserved or not. Of course, the other option is to say that, of course, measurement apparatuses are no more than a collection of quantum particles, so they, of course, can be described quantum mechanically. But if one does that, then in order to include them and claim that energy is conserved, one would need to have exactly the same energy at each step, for example, at each step of this two-step process that I described. But if this is the case, then we would be claiming that the state of the whole system is an eigenstate of the Hamiltonian, and things would not evolve. So you would not be able to perform these measurements I was talking about. So if you want to claim that including the apparatuses in a quantum mechanical description solves this non-conservation, then you would not be able to explain why things actually change when time goes on. So that seems to be a problem. And of course, if in the other hand one wants to have non-trivial evolution, then you would not be on an energy eigenstate, and you would not be able to define the value of energy. Okay. Right, so I think this is a too strict way of looking at things. So in order to move on, to say something more about that, one could opt for the following, to say, no, okay, so let's say that we initially start on a state that is not an energy eigenstate, but we start in a state which has a very small initial energy uncertainty. And the question one asks is if, so once we have this energy uncertainty, then there's a possibility of non-trivial evolution to happen. But the question is then if it is possible for energy to eventually get out of this small range which is allowed by this initial uncertainty. And okay, so first of all, it's clear if we do this that this will not occur, that energy will never wander outside this allowed energy range during unitary evolution, or even in the course of an energy measurement. If we have that system, let it evolve unitarily, then it will not wander outside of this initial range. And if we go and measure energy, then we will find one of the possible energies within that range, so we will not wander out. But the interesting question is what happens during measurements of quantities that do not commute with the Hamiltonian. And to answer this question, to really rigorously answer if during those kind of measurements the energy can jump outside of that range, one would need to have a detailed description of what happens during quantum measurements when one goes and measures. And the problem is that at least using the standard interpretation of quantum mechanics, we do not have a clear description of these quantum collapses. And the conclusion is that the vagueness associated with collapses within the standard formalism gets in the way of a rigorous assessment of this question. Okay, so Okay, so I'll come back to that point, and as I said in my plan, we will consider alternative interpretations. For now, let me consider another simple example that illustrates the problems regarding energy conservation in a non-relativistic context. So to do that, consider now this state, which is an let's say an EPR-like state of two particles which are entangled, but in which so, for example, we can consider we have, as in the EPR standard scenario, two particles that are created, and then each one flies to a different direction. But what we have in this state is an entanglement in energy states. So we have either particle A having energy E1 and particle B having energy E2, or the other way around. And of course, it is clear that the total energy of this system is E1 plus E2, but neither A nor B has a well-defined value of energy. And the question is, of course, what happens if I go and I measure, let's say, the energy of particle A? And well, okay, so the first thing that we notice that if we do that, the expectation value of the energy of A will jump from this combination to either E1 or E2, which the possible results is each with a 50% chance of occurring. And so the interesting thing to notice is that this measurement in the energy of A not only makes the energy of A to jump from this expectation value to one of these two, but also induces a jump in the energy of B. So before we were considering the idea of including the measurement apparatuses to resolve these problems with energy conservation, but it's clear with this example that if the measurement apparatuses resolve the violation, then the mechanism would have to work non-locally, because this example we measured the energy of one of the particles, and that made the other particle to acquire well-defined energy, and there was no apparatus there to inject the missing energy or to absorb it. So this mechanism, if it really works, it would have to do so non-locally. Of course, we have to take all this with a grain of salt, because in all I've said about this example, I have been thinking of energy as localized in either here or there. I was saying, okay, the apparatus would need to be there to inject the energy to particle B. But of course, this is not obvious in this quantum context. For example, in this initial state, I said that total energy is perfectly well defined, but I would be hard-pressed to explain or to say where the energy is located in that state. It's not that the one particle has some of the energy and the other part. So it's not clear in this context that one can think of energy as localized anywhere. All right. So what can I conclude about with what we've said so far regarding this non-relativistic quantum context? I think that the main conclusion is that, in general, the ambiguous nature of the standard formalism, in particular regarding quantum collapses, does not allow for a definite or rigorous answer to the conservation issue. And in particular, it seems hard to explicitly show that energy is not conserved, but at the same time, it is hard to show that it is. So one simply cannot resolve the issue. What is important to note is that this inability to resolve the non-conservation issue does not lead in any way to internal inconsistencies or stuff like that. So we can perfectly well use quantum mechanics to do all sorts of stuff, even if energy is not conserved, or even if you cannot resolve the question as regarding conservation of energy, etc. Okay, so this is the case in the non-relativistic scenario, and next we will explore what happens in relativistic quantum context. Okay, so of course one goes to relativistic quantum context, so one thinks about quantum field theories, and the question is, what can we say about energy conservation in quantum field theory? The first thought probably is the following, at least in the context of Minkowski spacetime. We have Nether's theorem, and it guarantees conservation laws in that context. But things are more complicated because in the context of quantum field theory, what Nether implies are conservation equations in terms of operators, but not in terms of actual physical quantities, which is the problem we had in the non-relativistic case. And the problem, as we explained, as we saw in concrete examples, is that a conservation equation in terms of operators does not directly or easily translate into actual physical conserved quantities. And moreover, of course, even if this would work, this would be ignoring quantum collapses, which complicate matters enormously. What about going to quantum field theories on curved spacetimes? Well, of course, things get even worse. On top of what I've said regarding quantum field theory on Minkowski spacetime, we have the fact that generically we will not have temporal symmetries, so in that case, of course, we would not even expect energy conservation to obtain. And again, what to make of all this? Is this a problem? And again, as in the non-relativistic context, this does not seem to be a problem. At least there's no problems regarding self-consistency because of this. And as with non-relativistic formalism, we can perfectly well use this formalism to do all sorts of stuff, even in the absence of exact conservation laws. Okay? Sure.
So even, am I right? Even in the non-relativistic case, one would expect the expectation value of the energy to be conserved. I mean, as long as the system isn't entangled with something else, right?
It is conserved during unitary evolution. The expectation value is. So expectation value of any constant of motion is conserved during unitary evolution. Sure. But
it is during the...
Sorry?
You don't think it is during measurement?
No, I know it isn't. Actually, I showed it isn't. So you start... So these examples... so in this example, you start with a expectation value for the energy to be this, and after measurement, it's either this or that.
Oh, that's why I said it for an unentangled subsystem. So the whole, the expectation
this is not entangled with anything. It's just like a simple particle.
Oh, sorry, yeah, right.
So it's a single particle. It's initially on an energy superposition of energy eigenstates.
Sorry, I didn't mean but you expect it to work statistically, though, right?
So probably statistically, I'm not sure exactly what you have in mind with that, but yeah, that's what
I'm thinking. I mean, at the ensemble level, you're going to end up with half of them with one energy and half with the other energy. So for the ensemble, there's going to be...
That's true during unitary evolution. Once you start measuring stuff, I'm not sure that that is the case.
If I apply the Born rule to that case, it will, right? I'll end up half.
Yeah, the Born rule, sure, but
in the limit of infinite, infinite things, your average should converge to that. But you measure 5, then.
Yeah. Sure. But, okay. But
yeah, I mean, if that's what you have in mind, sort of yeah, then I agree.
Okay.
All right. So, where were we? Okay. So I was just saying that this not having an energy conservation loss in quantum field theory does not imply any sorts of inconsistencies or stuff like that. So we can live with it. Of course, things get much more interesting once one tries to include a back reaction into the picture. So up until now, I was thinking of doing quantum field theory on a fixed, probably curved, but fixed backgrounds. So what happens if one includes a back reaction? And well, the obvious problem with trying to explore this question is that we do not know how to include back reaction. We do not have a quantum theory of gravity that does this. But still, if one wants to explore the conservation or non-conservation issue in this context, there are a few things that one can say. So first off, we know that the very notion of conservation only makes sense in a context with space and time. So a thing is conserved if it is conserved in time. So if you don't even have a time, then it's not clear what one would be talking about. And the second point is that even if one is considering a quantum theory of gravity that does not have space and or time at the fundamental level, this quantum gravity has to at some point make contacts with semiclassical scenarios, two scenarios in which we know that they work, so any theory to recover to be empirically adequate has to at some point, any theory of quantum gravity to be empirically adequate has to at some point recover semiclassical scenarios. So let's consider these semiclassical scenarios. Let me explain exactly what I have in mind. So the basic equation of these semiclassical scenarios is this equation. So the idea is to couple a completely classical space-time to the expectation value of some quantum field. And of course, due to the Bianchi identities, the left-hand side of this equation has a divergence equal to 0, exactly. However, there's nothing forcing the right-hand side of this equation to have zero divergence, particularly during quantum collapses. So, at least during measurements, this equation seems to be inconsistent. And the question is if this constitutes a fatal blow for this program, if this just shows that there's nothing interesting one can do with this equation. And of course, over the years, the applicability or even self-consistency of this program has been called into question many times. And so let's explore that a bit. So there's this famous paper from the 80s, I believe, by Page and Geithler. And in the paper, they report an actual experiment that they performed. And the basic idea of the experiment is the following. One considers some quantum event, for example, one has a spin 1/2 particle and it spin up in the z direction, and then it measures the spin along x. And with the result of that quantum event, one determines if a macroscopic sphere moves either to the right or to the left. And then one measures the gravitational field of such an object with a torsion balance. And so they actually went and performed this experiment. The idea is that when one measures the spin, it will, according to quantum mechanics, go into a superposition of going to the right and to the left. This will translate into the macroscopic sphere going to a superposition of going to the right or to the left. And if semiclassical gravity is the case, then what one should measure, because what one puts here is the expectation value. So what one would measure is the torsion balance not deviating either to the right or to the left. I don't know, that's like the general idea. And of course, they did the experiment, and the result was what one would expect. One, of course, has the torsion balance moving either to the right or to the left. And what do they conclude? By doing this experiment, they conclude the following. First, so they consider two options. They consider a quantum theory either undergoing collapses, a quantum theory that includes quantum collapses, and one theory that quantum theory that does not. So they say if quantum theory includes collapses, then the theory is if there are no collapses, then the theory is contradicted by experiment because of what I said. If there are no collapses, then the expectation value of the system would be symmetric between right and left, and then the torsion balance would not move, but it does. So if there are no collapses, the theory is inconsistent with the experiment. And if there are collapses on the other hand, then the divergence of the right-hand side is not zero, and the theory is inconsistent. Okay, so these are the two options. And of course this, well, at least to me, it seems to be a strong argument against semiclassical gravity, but I do not think it is a conclusive argument against it. Why? Number one, it's clear that the treatment of quantum collapses in the paper is not very sophisticated, so they have this idea of either it collapses or not, but it's not like really clear. Of course, there's lots of work around that question, and they don't engage with that discussion. And in more detail, I think that it's useful to recognize that what they detect are two potential problems with the semi-classical formalism, which are the following. The first one is that, as I already said, that during collapses, the divergence of the expectation value might not be zero, which is required for the theory to be self-consistent. And the second problem is that certain states with large dispersions in TAB might lead to empirical problems with formalism. Okay? So these are the two issues that are brought into light by this experiment. So what can we say regarding each of them? Regarding the first one, of course, it is clear that this lack of self-consistency is an important problem, but of course it's fatal if one is interested in taking semi-classical gravity as the fundamental theory. But if one wants to take it just as an effective description of the system, which one knows it's not the ultimate exact equation, then it seems that one can use it in an effective way. All this is analogous to the way in which we use, for example, the Navier-Stokes equations, which we know that they break down when, for example, I don't know, an ocean wave breaks in the beach and there's foam formed and stuff like that. Of course, at that point, the Navier-Stokes equations are useless. But of course, that does not mean that they are very useful in effectively describing the fluid in a large range of circumstances. So if one wants, one can do the same or try to do the same regarding the semi-classical equations. You know, say, okay, they break down. In particular, for example, they break down when collapses occur, but that does not mean that they are useless. And what about the second point, this idea of the equations not being empirically adequate for certain states of large dispersion in TAB? And the key question, I think, is if it is in fact possible to construct these states which would make the theory empirically inadequate, because it's not clear that in fact one can, of course, one can think of a state that would violate or would make the theory clearly at odds with the experience, but if one is unable to create that state in the laboratory, then there seems to be no problem. So, for instance, one could try to argue that the coherence gets in the way of constructing, for example, that example of this ball being in a superposition of being to the right and to the left. So if one cannot create that state, then there's no problem. The problem with this particular explanation using the coherence is that, again, to evaluate that statement, one would need to know much more details regarding standard interpretation, which are simply not available because of the vagueness of the whole thing. So one cannot, at this point, do a rigorous assessment of the issue. That's why, in order to go on, I think it's necessary to explore the status of energy conservation in the context of viable alternatives to the standard formalism. And in particular, I will consider these three, which are, I would say, the most serious contenders, which are objective collapse models, pilot wave theory, and Everettian frameworks. And so the idea is to explore the conservation issue in each of them, and also to explore implications for semi-classical gravity, okay, regarding what we find. Okay, so how am I doing in time?
23 minutes.
Okay,
including questions.
Including questions.
Including questions. Okay, I'm good. All right, so briefly explain what these objective collapse models are. So the idea of these models, they were developed in the 80s to solve the measurement problem in quantum mechanics, and the idea is to add stochastic nonlinear terms to the Schrödinger equation to construct a single evolution quantum equation that somehow combines the unitary evolution and the collapses and does it in an observer-independent way. And concrete examples of these models are the GRW model or CSL. GRW is the first one that was like fully developed, and basic idea is that you have a system of quantum particles, and you postulate that they evolve unitarily in general, but that each of them has some probability of undergoing these localization events. So are these events in which the wave function of the particles gets highly localized, and after that the unitary evolution continues. And well, one can show that proposing that one can somehow explain why when we measure things collapse, etc., and do so without invoking the notion of an external observer or treating measurement in a different way. Another example is CSL, which in a way is a version of GRW in which these discrete collapses are made continuous. So we have some sort of continuous noise that is driving things into eigenstates of a so-called collapse operator. And okay, so that's a general idea of these models. And an initial possible worry with these models is that they do not lead systems to eigenstates or eigenvectors of the so-called collapse operator. So I was saying, for example, in GRW you get highly localized states, but you don't get particles localized to a point. And that would seem to be a problem, because exactly what we wanted is to explain why things, for example, get localized when we measure them and stuff like that. And there are some possible solutions to this apparent problem. The first one is to substitute this so-called eigenvalue-eigenvector rule, which states basically that a system has a well-defined value for a property if and only if its state is an eigenstate of the corresponding operator. And the idea is to substitute that rule. Of course, if we have this rule, then we would be in a problem if states never collapse to eigenvectors. Then particles would never have well-defined values for properties. But the idea is to substitute this rule by this so-called fuzzy link. And the idea is to somehow relax this constraint and to allow for a small deviation from eigenstates and still assign well-defined values. And the other alternative is to introduce so-called primitive ontologies. So the idea is to construct some quantity that one postulates to be what's actually there outside in the world according to the theory. And concrete examples of these primitive ontologies are this flash ontology, which the idea is to associate the centers of these GRW collapses with what's actually out there, or this so-called mass ontology, which the idea is to interpret the expectation value of the mass operator as an actual mass density which lives out there in the world. Okay, so what happens regarding energy conservation within these models? So, as is well known, these models do not conserve energy. In particular, the expectation value of energy is not conserved during the evolution of these equations. So, for example, if a wave function undergoes a GRW collapse, it localizes to a smaller region, and it's clear when that happens, then the expected value of energy increases. And the question is, what are we to make about this non-conservation? And of course, to answer that, we would first need to explore how energy is defined within these models. We haven't said anything about that, and there seem to be two obvious options. The first one is to use a fuzzy link to define energy. So, as I was saying, to say that a system has energy, not if it's in an energy eigenstate, but if it's sufficiently close. And the other is somehow use the primitive ontology to define the energy of a system. Okay, but we wanted to explore the semiclassical program, so for that we need a relativistic model. So what about relativistic objective collapse models? They have been constructed recently, so there are at least two examples, this relativistic GRW and relativistic CSL. What about the possible primitive ontology for these theories? And a very nice option is to take the expectation value not of mass as before, but as of energy momentum tensor, And the nice thing of doing that is that with that ontology, the semi-classical treatment becomes very natural because, as I was saying, the primitive ontology is what one claims exists out there in the world. So that's what one would think that is natural to associate or to couple to GAB. And what about the two problems we encountered with semi-classical gravity? So we had this self-consistency issue and the issue of large dispersions in TAB. Could these models help you with these problems? Regarding the first one, there's not much one can do because, as I was saying, energy is not conserved, or at least the expectation value of energy is not conserved in these models. So the divergence of TAB generically is not, of the expectation value of TAB generically is not zero. But as I said, one can still explore them and use them as effective descriptions. And what about the second issue? Well, as I said, these models are designed to suppress macroscopic superpositions. And in particular, at the relativistic level, one can construct models in which the collapse operator, or the operator that it's not allowed, or that for which superpositions are killed, can be directly TAB. So if we do that, we directly avoid the problematic dispersions that could lead to empirical problems. So a collapsed model with TAB as a collapse operator would seem to never lead to problems of the sort that the experiment I talked about was showing. Of course, one must know that different components of TAB do not commute. So it's not clear. So what one can do is to somehow collapse to minimum uncertainty pockets of these different components or something like that. Okay, so let's move on to pilot wave. So pilot wave theory, at least in the non-relativistic version, states the following: to describe the state of a system, one needs not only the wave function but also the positions of the particles. The dynamics are given by a Schrödinger equation for the wave function and by this so-called guiding equation for the positions of the particle. And as is well known, hidden variable theories in general and pilot wave theory in concrete is non-contextual. It's contextual, which means that the results of measurements of properties other than the positions or the wave function depend on the experimental arrangement. So, given that energy is contextual, there seems to be no option for it to be conserved. So, the question is if it is possible to construct a non-contextual energy within these models. So, maybe the first thought is to use only the wave function to do so. So, one can use the eigenvalue of the vector link or the expectation value of the Hamiltonian to define an energy. And that would work, that would give you a conserved quantity, but the problem is that that would completely ignore the positions of the particles, which are a big part of the system. So it seems to be a non-very attractive option. So one can think of constructing an energy using only the particles. So first thing that comes to mind is this classical equation for energy, but of course this is not conserved during evolution. So to improve on that, one can add this so-called quantum potential, and by doing so, this is a quantity that is conserved during evolution, but only if the partial derivative of q with respect to t equals 0. And the problem is that this is not the case even for systems in which you would expect energy conservation to occur. So the upshot is that we do not have a nice way to define an energy which is conserved during standard pilot wave evolution. Okay, again, what happens to explore the semi-classical regime, we wonder about relativistic versions of pilot wave. So there are quantum field theories within the pilot wave framework, which you have a unitarily evolving wave functional, which is complemented with either fields or particles. And it's important to note that this whole program requires a preferred foliation, which is not a problem. We can discuss about that. So a concrete example, if we have a scalar field on the space-time GAD, one has a functional Schrödinger equation for the wave functional. psi, and then a concrete actual field configuration that evolves according to an appropriate guide equation. And so that works well, but what happens regarding energy conservation? Well, the upshot is that the status does not change in the following sense. One can construct a energy momentum tensor for this field, the actual field, and one can show that that it does not have zero divergence. So, what about semi-classical gravity? Well, there's an attractive option, which is to couple the classical space-time with this actual field configuration. So we have an attractive way to construct, which is not exactly the semi-classical equation we had before. In that one, I would need to put here the expectation value of the wave function, but this is not it. For example, the wave function can be in a superposition of the ball being to the right or to the left, and this thing will actually be either on the right or the left. So it's a different equation than the semi-classical one, but it's an attractive option given this framework. And how does it fare regarding the problems we encountered with semi-classical gravity? Well, as I said, it does not seem to address the self-consistency issue. The DAB is not...
12 minutes is left.
Okay, 1 minute. Okay, so let me quickly conclude. Okay, so... okay, so just 1 minute about this. So it does not address the self-consistency issue, but the dispersion one seems to be solved, at least in this sense, that you're not coupling to the expectation value, but something else. What about Everettian frameworks? Okay, so let me just say 30 seconds about the Everettian frameworks and I conclude. Okay, so the idea here is that one would think that in the Everettian framework one would have no problem regarding conservation because you have no hidden variables and only unitary evolution. So everything seems to work well. But the problem is that once one tries to couple space-time and matter content, one notes that one has to do that branch by branch. You cannot couple like a single space-time for every branch. If so, you would run into problems as the one exemplified by the experiment I described. So at the end, what you have is a description in each branch, which does undergoes at least temporarily non-unitary evolution, and you're back exactly the same problems that you have in the standard non-relativistic quantum mechanics. So Everettian frameworks do not seem to help much. So I think you can just read my conclusions and I'll stop.
We have 10 minutes for question and answers.
Is there any way to assign some operational meaning to the violations of energy conservation? For example, can I build a machine that extracts energy for free?
Let me say two things. First of all, I think as I showed in the non-relativistic quantum context, it's not the same to actually have violations of energy conservation, to say that it's not even clear that the question can be answered either way. So in that context, for example, it's not clear to me that you can extract that energy, because it's not that you start with some energy and you end up with a different energy. It's either that you go from a state in which energy is not well defined to one in which it is, or the other way around, or that you have to include the measuring apparatus and you don't know how to use it to do that. So it's not that we have clear violations of energy conservation, it's just that we cannot show that energy is actually conserved. So that's my first question, my first answer. The second answer, maybe Daniel wants to say more about that, but he has a proposal to actually use this energy that is not conserved to explain some stuff in the cosmological setting. I don't know, should I say something about that? Or? Okay, so Daniel will talk about that. So,
Confirmation.
So I think in a paper that Craig Callender and I wrote, a while back, we kind of talked about these things, and I just wonder about the self-consistency sort of problem for semi-classical gravity. I think the idea we had was, you know, the way you're supposed to read that equation is it's not going to hold at every point of space-time, but it's going to be holding in regions where there aren't collapses happening, and then there's going to be discontinuities in there. And I don't quite see why that's a failure of sort of failure of self-consistency.
Yeah, it's not clear to me.
I'm going to get the divergenceless part, you know, where there aren't collapses. That was sort of
yeah, but it's not clear to me that collapses occur in space-time points, right? Because collapses occur to fields, which are things that are defined on hypersurfaces. So it's not that it collapses here and it doesn't here, right? This global thing.
So I had sort of regions, so there would be kind of like boundaries around the regions. I think that was the kind of picture.
I
think about it.
I will show a formalism that includes what you just said.
Okay. The point, yeah, there's sort of something weird happening there, but I don't quite see that it's inconsistent. Doesn't seem quite the right way, the way I would put it. Somehow.
Well, at least at some point, it's not consistent throughout the whole manifold. Let's say.
Yeah, I mean, if you want to take that equation as fundamental equation of nature, then it has to be satisfied at every point, and if it isn't, then that's a problem.
Kind of pretty strong metaphysical. There's a sort of metaphysical assumption about what fundamental law has to look like.
Right.
But yeah.
Okay.
Thank you. One of the problems that you were addressing in the quantum mechanics case has to do with energy conservation and thinking about the measurement device itself actually participating in either absorbing or perhaps producing the leftover energy. And then you complained, well then your energy, your system measurement device, if it itself doesn't change in energy, you made this comment, well then there's like a static situation there and nothing's evolving, nothing's changing. You said something like this.
Yeah, but the idea was that if the claim is that by including the measurement apparatus, then you recover energy conservation, which is a comment that you often hear at least in physics departments. Then the point is that at every stage, if you consider the whole system, the closed system, which is the system plus the apparatus, then the whole thing has to be on an energy eigenstate of the complete Hamiltonian. And if that's the case, then it will not evolve, right?
Sure. The whole system might not evolve, but couldn't we still insist that the parts of the system change?
No. The whole system doesn't evolve, then nothing evolves, not even parts. Yeah.
Is there any? Yes.
What's your overall takeaway? Like, how should we regard the principle?
Well, I think that if you don't include back reaction, if you don't go to the semi-classical regime, then there's simply no problem. I mean, you can just go on living and doing physics without having this principle of energy conservation. The problem arises when you have to, when you want to go to this semi-classical regime in which for self-consistency you need the expectation value to be divergenceless. So at that point you have to start thinking a bit harder, which does not mean that you have to throw the whole program into the garbage, but you have to at least work a bit harder. But before that, you can just move on. Just have it clear that energy is not conserved in our universe.
Is there a question? Yes, but does that then mean that sort of both horns of the dilemma by Page and Gauke are not conclusive, really? Because on the one hand, the argument that if there is collapse, it's too quick, it seems, because they have a somewhat simplistic understanding of what a collapse is. but also the argument that if there's no collapse, it turns out actually much more complicated and depends on how, you know, on the more work you do, I suppose, to really turn this into...
Yeah, I think I would agree. I think that the whole analysis is simplistic. And, yeah, the true answer is that things are much more complicated.
This is rather a question of understanding. So why did you carry out the analysis at the level of conserved current and not at the level of symmetries?
I mean, of course, these two things are related, and my claim was that in the context of quantum field theory, if you have a symmetry, then you will have a conserved current. But you will have that only at the level of operators. And the question is if that directly translates into actual conserved physical quantities. And my claim is that it does not. So, yeah, I mean, symmetries and conserved currents are, of course, related. But yeah,
I'm just wondering because you stress it so much at the beginning. So, yeah, but I see the point if you carry out the measurement, it's hard to keep track of the symmetries, but maybe that's exactly the one way you could enter through an analysis of symmetries, right? So just by taking care of the symmetries and wondering how much of the symmetries still can be kept when dealing with different applications, you could equally, I mean, is there a sense of conservation available or not?
No, I think, my point is that even if you have exact symmetries in the quantum context, you will not have conservation equations for actual physical quantities.
Okay.
If there is no extra question, and because the time is almost over, is Afnaz Elias, thank you.